The only way we know at the moment to find the dimension of a vector space is to actually find a basis for that vector space and then find how many elements it has. That's what we're going to be doing in this video. We're actually going to begin with a special case, which is not quite covered by the definition of dimension which we made last time. So I'm going to add it here. So definition. If you have the zero vector space, then its dimension is going to be defined to be 0. So very often we think about the zero subspace of a vector space, and I'd like to have a definition of the dimension of that. And it's not quite clear how that fits in, because it's not clear what a basis of the zero vector space should be. So let's just make a definition once and for all that the dimension of the zero subspace of a vector space is 0. Alright, so we're ready to start, and all we're going to do, as I say in this video, is to compute some examples of vector spaces, so of the dimensions of vector spaces. So let's begin with the vector space f to the n. So f is some field, it might be the real numbers or the complex numbers or something else, and f to the n is the vector space of all height n column vectors whose entries come from f. So as we've seen before, it has a basis consisting of E1, which is this vector, and then E2, which is the next vector with a 1 in position 2, and so on up to En, which is 0, 0, 0, all the way down to 0, and then a 1 in the last place. We proved that this was a basis, and we called it the standard basis. So it follows that the dimension of f to the n is n. And this fits with the informal idea that the dimension of a vector space over a field f is how many independent parameters from f you need to specify an element of that vector space. To describe an element of f to the n, you need n different elements of f, because that's what an element of f to the n looks like. It looks like a column vector containing n different parameters from f. So the informal idea of the dimension of a vector space fits with what we just calculated. And let's look at a slight generalization of this. So we're going to now look at m by n matrices. So the dimension of the vector space of all m by n matrices whose entries come from f is going to be m times n, because it has a basis Eij, where I runs between 1 and m, and j runs between 1 and n. So there are m times n different possibilities for those things. And here what I mean by Eij is the matrix with a 1 in position ij. So its ij entry is 1 and 0s everywhere else. Now we haven't proved this, but we did at least do an example of this in our lecture about bases. So we did the case where m equals n equals 2 and where the field was the real numbers a few lectures ago. And in that case, the basis was E11, which was this, E12, which was that, E21, which is this, and E22, which is this. So the dimension there is 4, which is 2 times 2, and you can prove in general that the EIJs form a basis in exactly the same way that we did when we did the 2 by 2 case over the real numbers. We're now going to do a slightly harder find the dimension problem. So let's suppose that we are sitting in an exam perhaps, and somebody asks us the following question, which is find a basis of M, which is defined to be a set of all 2 by 2 matrices A, B, C, D in M 2 by 2 of the reals, such that A plus D equals 0. And find the dimension of M. Alright, so that's the problem we're going to try and solve. Let's notice first of all, for this problem to even make sense, M had better be a vector space. And it is a vector space. In fact, it's a subspace of M 2 by 2 of R. And subspaces are, of course, vector spaces in their own right. So let me just say that you should prove, I'm not going to do it, but you should do this. You should prove that M is a subspace of M 2 by 2 of R, so that it's a vector space in its own right, and it makes sense to ask what its basis, what its dimension is, and to find a basis. All right, so assuming that you've done that, let's start with solving this problem. How might we do it? Well, I mean, we have to look for a basis of this, and it's not really clear how we do that. So let's just think a little bit. I mean, what does an element of this vector space M look like? So any element of M equals A, B, C minus A for some numbers A, B, and C, real numbers A, B, and C. So that's true by the definition of M. And that is a useful thing for us to write down because it gives us a clue. It helps us to find a spanning set at least for M, because we could notice that this arbitrary element A, B, C minus A of M is equal to A times 1, 0, 0 minus 1 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0, and importantly, those three matrices, so this one, and this one, are all elements of M. If you're looking for a basis of M, then the most basic thing, most basic property that basis must have is that the elements of that basis must be elements of M. So it's extremely important that when we try and find our basis, we check this most basic requirement that they've actually got to be elements of M. So we should notice, first of all, these things are elements of M. And let's give them some names for now. We're going to call this H, and this E, and this F. And we're going to notice that those things are in M. So now I've observed that those are elements of M. We can notice we can say that what we get straight away from this is that H and E and F are a spanning set for M. Right, it follows straight away, because what this equation here tells you is precisely that every element of M can be written as a linear combination of H and E and F. So straight away, just by writing down the definition of an element of M, we have found a spanning set. And if we can prove that that spanning set is also linearly independent, then it will actually be a basis and would have done what we wanted to do. Oops, wrong colour. So next question is, are these three matrices H, E and F linearly independent? Again, this is actually an easy calculation, because to find if they're linearly independent, we have to take a linear combination of H, E and F which is equal to the 0 vector in our vector space, and then prove that the coefficients in that linear combination must actually be 0. So let's take that linear combination. If A times H plus B times E plus C times F is equal to the 0 vector in our vector space, which is the 2 by 2 0 vector, then just expanding this left-hand side here to just doing the matrix addition, doing the scalar multiplications, what we get out of that is A minus A, B, C equal to 0, 0, 0, 0. Okay, well then it follows straight away, right? A equals 0, B equals 0, C equals 0. Now we've proved that H, E and F is linearly independent, because we showed that if you had a linear combination of them equal to the 0 vector, then all of the coefficients in that linear combination must be 0. So we've shown H, E, F is linearly independent and that it's a spanning set for M. Therefore, it's a basis of M. Finally, the last part of the question was find the dimension of M, but of course that's easy. The dimension is the size of a basis, any basis, and we've just found a basis of size 3. Okay, that's it. If you'd like to see more examples of basis calculations and dimension calculations, you can find a couple more examples written down in the online notes for this section.